5 pit stocks. We call them research nuggets. They have been historically very successful events. So this section is created by the students and it's meant for the students. And you will have the chance to see how students in this program develop their own ability to do research. And also, importantly, as Uli said, they also create their ability to communicate it properly, and you will have the chance to see that. So I'll just step out of the way. I'll introduce the first speaker, David Domingo. He's been advised by Professor Kannan. So David will talk about accelerating storage recovery. David, the floor is yours.
Thank you. I hope you can all see my screen and hear me properly. All right. Okay. So welcome. Hi, I'm David Domingo, and I'm a third-year PhD student, and I'm here to present my research towards storage adaptability, and one of the projects I've worked on towards my research goals, which involves accelerating and adapting storage recovery for modern storage. So I want to start off by introducing you to an issue within the expanding space of storage. Right, so you're all familiar with the classic hard drive, but now we have more modern storage technologies such as solid-state drives and non-volatile memories that provide lower latencies and higher bandwidth capabilities. In addition, you can utilize multiple of the same storage device in multiple storage setups such as RAID in order to get better performance or data integrity. And as of recently, there's actually been a rise in hybrid storage setups that combine different storage devices in order to get better performance. So with all these setups coupled with all the different file systems you can use to manage the way data is stored on these devices, we can see that there is an exponential number of storage configurations we can use, each providing differing amounts of storage performance. So the main question is, whatever storage configuration we use, how do we ensure that applications extract the best performance? So the naive approach to ensure good storage performance is to actually manually tune the applications. For example, we might want to use more than one thread to do I/O in order to take advantage of available bandwidth. However, this approach is not ideal for a couple of reasons. First, manual tuning is tedious and unfortunately requires extensive knowledge of the application and storage capabilities. Second, manual tuning is inefficient and unportable, and the application will have to be retuned if deployed on different storage hardware. And finally, manual tuning leaves a lot of room for error, and misconfigured applications could lead to underutilized storage devices and reduce return on storage investments. So the goal of my work is to minimize this tedious work and enable efficient storage integration. We should be able to automatically get good application performance for a given setup and mitigate any manual tuning and modifications to the applications. So this is something that I envision out of like a sci-fi movie where storage modules are plug and play and automatically get good performance. And towards this, I'm looking into the idea of storage adaptability. So the idea that applications can adapt to the underlying resources and automatically extract the best performance with little to no effort. This will allow applications to be more portable and efficient and allow application developers to focus on more important things like business logic. So where does storage recovery fit into this? So we found out that storage recovery tools such as file system checkers are actually great candidates to explore some of these ideas for storage adaptability. For those that are unfamiliar, file system checkers repair corrupted file systems by scanning through all on-disk metadata and fixing errors along the way. And these checkers are ideal because first, because the checker has to scan the whole file system, the checker requires a lot of I/O, which makes a good representative for I/O intensive applications. Second, file system checkers have been seen to be highly unoptimized and run notoriously long because they were built in the age of hard disks and don't effectively exploit any I/O parallelism. Lastly, these checkers are used in a variety of environments on different storage setups as well as system configurations and can be ran in isolation or sometimes simultaneously with other applications. So knowing this, we want to answer the following questions. Can we exploit modern storage capabilities and accelerate recovery? And also, can we make file system checking more portable to different environments and make it easier to bear with for system administrators? So this is what we did with our work, PFSEK, a parallel file system checker that we built based on FSEK for ext file systems. In order to accelerate checking, we took the original 5 passes which traditionally run serially and utilized multiple thread pools and queues to introduce data and pipeline parallelism. This enables PFSEK to use multiple threads to exploit available bandwidth on modern storage by not only performing more I/O within each pass, but across passes. We also implemented a dynamic thread scheduler, which migrates threads between passes based on the amount of outstanding work to be done in each pass. This enables PFSEK to adapt threading based on the constraints of the computational logic. Lastly, we implemented a resource-aware scheduler, which schedules and deschedules threads based on the available number of free CPUs. This enables PFSEK to adapt threading to available hardware resources. Altogether, these approaches enable PFSEK to increase I/O bandwidth utilization by up to 1.9x and show runtime improvements by up to 2.6x over the original FSEK for ext4. And it's able to do all of this without extensive tuning and minimal impact on other co-running applications. So for brevity, I won't go into much detail, but the impact of this work is that it was recently presented at the Usenix conference on file and storage technologies this year. And in addition, some of the performance improvements and fixes that resulted from our project has already been upstreamed to the kernel tools repo. And finally, there are already signs that the open source community has already started to implement some of the approaches from PFSEK, which is pretty cool. So what does this mean moving towards storage adaptability? So with PFSEK, we are able to prove that an application can be parallelized and mechanisms can be used to dynamically adapt the application to increase bandwidth utilization and dynamically adapt the application to available hardware resources. So now we're looking into ways to generalize some of our approaches and create frameworks not only to apply to other checking tools for other file systems, but also any IO-intensive applications in general. So I'd like to end by saying that what I just presented is just one of the many areas we've been researching here in the Rutgers Systems Research Lab under Sudarsun Kannan. Overall, our research aims to build scalable, efficient, and secure systems for handling storage and memory heterogeneity. You are free to contact me if you have any questions. And with that said, thank you for listening.
Thank you, David, and thank you for keeping the very strict time constraints. So unless anyone has any question, I'll now turn to the second student, Neelesh Kumar. I was fortunate to have Niles as one of my students since my very first semester in the department. So he did his master's in the lab. He continued as a PhD student, and he's now almost ready to graduate. So Niles, can you share your screen? And...
Okay. Can you see my screen?
Sure, yes, thank you.
Thanks for the introduction, Professor. So imagine a robotic arm restoring or even replacing your movements by using just your thought. Although it may seem like science fiction, our work over the past few years is making this a real possibility. So today I'll present our brain-informed learning models that learn movements and bring us one step closer to realizing our goal. Okay. So motor learning is a crucial aspect of biological intelligence, using which our brain learns or relearns how to move. We know since the 60s that there are specific neurons that control how we move by learning direction, speed, and other characteristics. So movement is learned by distinct neurons in our brain. And although there are many methods to record brain activity, EEG has long been the widely used, mainly because of its non-invasive way of acquiring brain signals. But for a long time, EEG has been hampered by poor spatial resolution, which makes it difficult for the state-of-the-art methods to decode it, due to their limited representation capacity and reliance on handcrafted features. The field of machine learning has witnessed the rise of deep networks that approximate complex functions with unsupervised feature learning. Our overarching goal is to leverage brain architectures for developing new deep network architectures that can learn movement from brain signals. And this is important because it allows us to use brain data to bypass the impairment and replace or restore the lost movements with a robotic limb. Specifically, our work targets learning movement from brain signals by developing artificial networks that are derived from brain architectures, hence making it a more natural fit for such problems. We then go one step further and learn the complex task of assessing cognitive engagement, which is crucial to ensure that subjects are performing the correct movements. we conducted an IRB-approved study in the lab where human subjects performed a motion task on the rehabilitation arm robot. As the subjects were moving, we were recording their brain activity, and the objective was to develop brain-inspired networks that can learn the various movement components from the brain activity, namely the direction, reaction time, and whether the movement was performed by the robot or the subject. We developed artificial networks that for the first time leverage knowledge of brain architecture and its neurophysiology in their design. And by being brain-derived, our network learned the movement components more accurately than the current state of the art. We also learned whether the subjects were cognitively engaged or not while performing movements, and again, our network achieved high accuracies. And it even predicted something that has never been quantified before, the continuous loss in engagement in real time. Now that our network follows the brain architectures and its learning mechanisms, it became natural for us to tackle a topic of intense research in machine learning these days, interpretability. We developed methods to understand where in the artificial network learning takes place, and strikingly, this artificial learning follows the patterns found in biological networks. A central goal in our lab is to develop spiking artificial networks that can co-learn with their biological counterpart. This introduces a new type of interaction between biological intelligence and artificial intelligence. And we are fortunate to be one of the handful research sites in the world to have a neuromorphic processor. These chips are hardware realizations of the biological neurons that communicate with each other through spikes. We designed brain-inspired spiking neural networks for EEG classification and deployed them on Intel's Loihi neuromorphic chip that we have in the lab. And our spiking neural networks outperformed the current deep neural networks. To conclude, we propose methods for brain-informed deep learning of movement for neurorehabilitation robots. Furthermore, through our interpretation techniques, we can understand how the brain learns these movements and use that knowledge to inform artificial learning. Here are some references. And lastly, I would like to thank all the excellent graduate and undergraduate students that I've worked with over the past few years, without whom these works would not see the light of the day. Thank you.
Thank you, Niles. And unless there's no question, there are no other questions for any questions. I'll now turn to Guido Tagliavini Ponce, who will give a talk on the stability and succiness in hashing. Guido is being advised by Professor Farach-Colton. Guido, the stage is yours.
All right, thank you so much for the introduction. My name is Guido, and I do research in theoretical computer science advised by Martin Farach-Colton, and I'm gonna talk a bit about great hash tables. So first of all, what is a hash table? So a hash table is just a dictionary data structure supporting 3 operations. You can insert a key associated to a value. You can delete a key and therefore its corresponding value. And you can also query a key and that will return you its value. So chances are all of you have already used hash tables at some point in your life because all popular programming languages have built-in implementations of hash tables. So what constitutes a good hash table? What properties do we want from them? So I want it to be fast, meaning that every operation runs in constant time with high probability. With high probability part means that it will run in this time almost every time. We also want it to be space efficient. And this could mean, for instance, that it uses O of n space. So for instance, if your hash table uses 3n space or 50n space, then it's space efficient. And for quite some time, we have known how to build hash tables with these properties. And interestingly, the first important step towards this goal, to achieving hash tables with this property, was taken by 3 very remarkable Rutgers faculty, namely Michael Fredman, Janos Komlosh, and Andres Zemeretti. They published in 1984 a paper of a hashing scheme that nowadays is known as FKS hashing. they did static perfect hashing. Static means that the table never changes, so there are really no insertions and deletions. And perfect hashing means that it has these two properties of being fast and space efficient. So there's a problem with this definition of space efficient, which is that when n, the number of elements in your hash table, is in the orders of tens of gigabytes, then suddenly 3n space could mean that your hash table no longer fits in your memory, your RAM. And so really what we want is a tighter definition of space efficiency, which is that it uses space 1 plus epsilon n space, where epsilon is a number that approaches 0 as n goes to infinity. So those are the two properties we want from any good hash table. So what are the properties we may ask from a hash table? Like what if we want not just a good, but a great hash table? So we want it to be stable, which means that once an element is inserted in the table, it is never moved. So you may know that some data structures every now and then move elements around to guarantee that their access is going to be efficient and also to compact the space. So in a stable hash table, we don't want to do that. So once an element is placed, it's going to remain there forever until it's deleted. So this has an important consequence, which is that we can have pointers to elements in the hash table, and they won't get invalidated. And this property is very important in practice. And to give you an example, the C++ standard actually requires, if you want to comply with this standard, it requires your hash table to be stable. Another property we want from a great hash table is low associativity. This is perhaps less popular, but not less really important, which is that each element can only be hashed to a few places in the table. And I don't want to get into the details of this definition, but so to give you an example, if an element can be hashed into 2 different slots of your table, you can remember which slot you have hashed that element to using only 1 bit, because there are only 2 choices. And so the consequence of this property is that we can encode the position of an element in very few bits. And so when you add up these 2 properties, stability gives you pointers that don't get invalidated, low associativity gives you tiny pointers, and so add them up and you get tiny pointers that will not get invalidated. And so, and this combination has very powerful applications. I will mention that in 2 slides. So very recently, we have developed and analyzed the first hash table with all of these properties. It's fast, space efficient, stable, and has low associativity, and even more that's beyond of this talk. And the challenge here is that some of these properties seem to be at odds with each other. And so this is like playing whack-a-mole, where it's easy to get 1 or 2 properties from this set, but it's really, really challenging to get all of them simultaneously. And the main analytical tool we use to analyze our hash table is balls and bins games. If you don't know what a balls and bins games is, don't worry, I'm happy to talk about that offline. Let me tell you that along the way, we solved the long-standing open problem about balls and bins games. And so all of this theory was originally motivated by a practical problem. We wanted to do address translation, which in the context of operative systems means to translate virtual addresses into physical addresses. And more specifically, we wanted to improve the TLB hit rate without paying the I/O and fragmentation costs of Linux huge pages. Again, if some of these words don't make sense to you, I'm happy to explain what they mean later on at the breakout sessions. So we have all this theoretical groundwork, and now we are building a system that has strong theoretical guarantees. And therefore, our research team is not only has theoreticians, but it also has OS researchers and architecture researchers. And we have in the theory side, Martin Farach-Colton there as well. And on the OS side, we have Professor Kannan. And so if you want to know more about this research, you can reach out to any of us. And if you have more questions, please direct them to me in the theory breakout session. Thank you.
Thank you, Guido, and sorry for mispronouncing your name.
No worry, nobody gets it right.
I have, like, the least I can say is I feel you. So let's go to our next speaker, Harsa Srimath Tirumala. He is being advised by Professor Allender. Harsha, the floor is yours. Minimum circuit size problem. You can unmute yourself because that's, yeah. Harsa, you have an issue, we can go with Honglu, Zhou, and then come back to you if you prefer.
Professor Harsha just told me that he has problems with internet and he'll try to fix it. So maybe we can proceed with the next participant.
Yeah. Yes, sure. Honglu.
Sure, I can start. I'm
Sure.
going to share my screen.
So Honglu is working with Professor Kapadia, and she will give us some hints on her research on multi-hop transformer for spatiotemporal reasoning.
Okay, thank you for introducing me. I'm going to start. So hi everyone, I'm currently a fourth year PhD student from Computer Science Department at Rutgers University, and topic of my talk today is multi-hop transformer for spatiotemporal reasoning. Okay. So our current neural networks, machine learning systems actually have truly made success on a variety of tasks such as machine translation, speech recognition, and computer vision. But in some sense, many of our current systems have approached things as a stimulus response task. Basically, you provide the input, then ask the model, could you produce the output as a kind of statistical association task? And this kind of tasks don't require deliberate thinking or reasoning. So how can we develop systems that are more intelligent than our current systems? And what can we do about reasoning? Well, reasoning in terms of humans is the ability to manipulate knowledge entities in terms of relations. Humans are subconsciously performing reasoning all the time. For example, when we are driving, we would first recognize the objects, which are the knowledge entities. And then we would form an understanding of relations between these knowledge entities. We have tons of real-world applications of reasoning, and for tasks like this, we really need a better notion of having knowledge and reasoning. And this is actually where our current models are lacking. Most current neural networks are just large correlation engines. They can easily be fooled by statistical superior patterns and dataset biases. For example, models can recognize action swimming even when the actor is masked out, because the models relied on the blue swimming pool, the sim bias. And the model can predict the action label changing the doorknob by simply recognizing the doorknob without paying attention to the actor or any temporal changes, because the donor is only associated with the label changing the donor in the dataset. And this is the dataset bias. So we really need a model that can flexibly deploy knowledge and reason. Otherwise, AI systems just cannot adapt to our real world, which is constantly changing. So how can reasoning be learned? So one inspiring viewpoint was proposed by Leopoldo, who suggested that the heart of reasoning is having the means for algebraically manipulating previous acquired knowledge in order to answer a new question. And reasoning can be achieved by deep learning. So central, he also mentioned that central to reasoning is the composition rules that guide the combination of trainable learning components to address new tasks. Chris Manning further suggested that building the right kind of inductive biases or structure priors into the models is the way to build composition rules for multi-step reasoning in the neural networks. And those successes include convolutions and gating that you can find in LSTMs and attention mechanisms. And our work falls into the last category. So this is a video related to our dataset. So I'm sure many of you knew about this game. So apparently even cats can solve this type of long-term spatiotemporal reasoning task, like locating the ball as the cups are shuffled. And we were using a synthetic dataset called Cater with a similar objective. And this is the Cater dataset. So this is a video dataset, and in this dataset, every video has multiple objects moving simultaneously. Objects have different kind of actions, and every video has a special object called Snitch, which is this golden object. And the task is called Snitch Localization. It means that you have to find out where the snitch is in the end of the video. And this task implicitly requires true spatiotemporal understanding and multi-step long-term compositional reasoning. So we propose Hopper, which is a universal multi-hop spatiotemporal reasoning model. If you're interested, please check out our iClear 21 paper, Hopper multi-hop transformer for spatiotemporal reasoning. The key here is basically we sort of imitate the human's way of doing step-by-step reasoning in this Hopper model. And we also released a new dataset called Cater Hard, which is a more difficult video dataset to avoid any model to achieve high performance by taking shortcut to only looking at the last few frames. And our model is also interpretable. So, for example, we found that in the first step, our model would first attend to the last visible snitch, and then in the next step, the model would attend to the container of the snitch or the occluder of the snitch in the next step. So reasoning is the next milestone in artificial intelligence, and it's very important. In our work, we use the great power of deep learning to achieve the spatiotemporal reasoning for the video understanding task. Yeah, so that's all. Thank you very much. If you have any questions, please feel free to email me. Thank you.
Thank you, Honglu, and thank you for your fast reaction time. Harsa, are you ready?
Yes, I believe so.
Yep. Okay.
So sorry about the confusion. So Neelesh is helping me share the slides. So once he starts sharing the screen, I should be good to go. Thank you, Neelesh. All right. So I'm Harsha. I'm a third-year PhD student working in theoretical computer science. My research advisor is Professor Eric Allender, and today I'm going to talk about the minimum circuit size problem and one-way functions. Right. So, the collaborators that I'm working with are Eric Allender, Mahdi Charakchi, Dimitrios Merisiotis, and Ilya Volkovich. And the presentation today is based on work I'm currently doing with my collaborators. All right, so what is the minimum circuit size problem? Well, the minimum circuit size problem is defined as follows. Essentially, you're given the truth table of some Boolean function as input. And the question that you're asked is there a circuit of size k, where k is some size parameter? So is there some circuit of size k which agrees with which computes f, right? So for a very easy to compute function, like let's say x1 or x2 or x3 all the way up to xn, you will have a small size circuit, let's say of size n-1 or n, which computes this. Whereas if you find more difficult functions, then of course you are unlikely to find small circuits that compute them. So these constitute the yes and no instances for the minimum circuit size problem. All right. And okay, so could you go back once? Thank you. So the focus of meta-complexity theory is to determine how hard it is to determine how hard problems are, right? So complexity theory talks about how hard a certain problem is, whether it's in P, NP, P space, you name it. Whereas meta-complexity theory talks about how hard it is to classify what is a hard problem and what is not a hard problem, right? And one result that we know for minimum circuit size problem is that it is in the complexity class NP, since the truth table provides us enough time to verify whether a certain claimed circuit indeed computes the function that we are talking about. Right. So next we are going to talk about the hardness results for MCSP. Hardness results for MCSP have been limited, primarily because it's such a fundamental problem that any hardness result for MCSP has very big consequences, right? So for example, one result due to Murray-Williams states that if MCSP is NP complete, then the complexity class X is not equal to the complexity class ZPP, which is a major open problem in computer science, right? So if someone wants to prove that MCSP is NP complete, then the proof for that should also include, the implication that X is not equal to ZPP. So any proof of NP completeness for MCSP is going to be, nothing like what we've seen so far. All right. So the next object of interest are one-way functions. What are one-way functions? As the name suggests, one-way functions are functions that are easy to compute, but they are hard to invert, right? By hard to invert, we essentially mean that any probabilistic polytime algorithm fails to invert a given function. Okay, so I mean, intuitively, all of right. So the definition for one-way function is as has been provided there. Basically, what we mean to say when we call a function one-way function, what we mean is that we are unable to invert. If you're given the function value, we are unable to successfully compute which input would have led to this function value with any reasonable probability, right? And why are one-way functions important? One-way functions have been proved to be necessary and sufficient for private key encryption, pseudo-random generators, pseudo-random functions, zero-knowledge proofs, and other such applications, right? So these are very fundamental objects whose existence has lots of consequences. Okay, so the relationship between one-way functions and NP. What is known? We know that if one-way functions exist, then P is not equal to NP, right? So if someone is able to establish the existence of one-way functions, then there is this whole, you're solving major open problems in computer science, and that's why it's not easy to establish the existence of one-way function without any other assumptions, right? Other implications of one-way functions include existence of one-way functions proves that the complexity class NP is not in BPP, and that the MCSP problem cannot be solved in polynomial time, right? What would we like to show? Sorry, could you go back to the previous? Yeah, we would like to base the existence of one-way functions on the hardness of some NP complete problem, right? So we know the first direction, that one-way functions implies NP is not in BPP. Now we would go for, I would ideally want to go for the opposite direction, which is if NP is not in BPP, then there exists one-way functions, right? And if we want to do this, picking MCSP will not work because we have just seen that it's not so easy to prove that it's NP complete. So we want to go for some other problem potentially, which will give us this, which will satisfy this objective. Okay, so recent work has shown that the existence of one-way functions is equivalent to the average case hardness of estimating the amount of information in a string. right? So this problem is known as the KT computation problem, and it asks, given a string, how much information does a string have? For example, a string which has just 1010101010 100 times has not much information, whereas think of a more random string 01100001010 and random numbers at each point. It has more uncertainty, more information in it as compared to the first string that we talked about, right? So this problem of computing exactly how much information there is in a string has been shown to be equivalent to the existence of one-way functions. The average case hardness of this problem is equivalent to the existence of one-way functions, right? This doesn't really solve the problem that we were interested in, because computing the KT complexity is not known to be NP hard. So, well, it's good progress, but it's not good enough. And in our current work, which is currently in progress, we are confident of making progress towards this objective. Essentially, what we do is we come up with a problem description which simultaneously captures MCSP as well as the KT computation problems, right? And why is this reasonable? Well, KT problem asks how much information there is in a string. MCSP asks how small a circuit can you come up with for a given truth table. So if your function has a small circuit, then intuitively it also has the truth table of the function also has a small description, namely the description of the circuit that resolves this function. So yeah, this is what we are working on currently to prove, and our work builds on techniques used in the recent paper by Liu Pass, which was responsible for the previous result, and some other hardness results for a slight variant of the MCSP problem. Thank you. This is all I had to say. If you have any questions, please feel free to reach out. And I'm sorry for my technical difficulties once again.
Thank you, Harsha. Thanks for delivering an excellent talk despite the technical problems, not because of their absence. So good job. So thanks and congratulations to all the speakers for the well-prepared talk.